Just okay, I will start. All right. So hello. This is Seishi Enomoto. I am working on working on the Science University Physics School of Physics. Today, I gave a lecture for the thermodynamics on cosmology. And today's topic is here. And one is about the thermodynamic variable in equilibrium state. And also, I defined some very important quantity about the effective degrees of freedom. And finally, I gave some application example for the using this thermal history of the universe. At first, actually, the universe at the very beginning, it was very hot. So the theory should be described by the thermodynamic picture. So to describe this this dynamics, actually, we use the distribution function, which is the by saying roughly the histogram of the particle for some momentum or something. So I define the distribution function by this form, like Bose-Einstein or the Fermi-Dirac distribution. So here the minus sign means the boson and plus sign is the fermion. And if you take the energy, I'm sorry, this is opposite. Sorry, this inequality is opposite. But if you take the small limit of energy, I'm sorry, it is correct. And if you take the energy is very larger than the temperature, then of course this part becomes very larger. Then exponential term becomes dominate. Then this plus minus one can be negligible. So this part is only remained. So in this case, the distribution is called as the Maxwell-Boltzmann equation. So it is used for non-relativistic particle as well. And we're saying roughly, if you take the non-relativistic limit, I mean if you expand this energy by the mass and the energy density, momentum, then this is also used for very broadly. So using this distribution function, then we can calculate the thermodynamic variable for some quantity. So we mainly we consider the number density and energy density and pressure are very well known in the thermodynamics on cosmology. So we define the number density can be derived by just the integration of the distribution function by momentum, three-dimensional momentum space, times this g is the degrees of freedom of the particle. So for example, if we want to consider the photon, then photon has the two mode of the polarization. So in the photon, this g is just a gamma, g gamma. I like the gamma is a photon, means the g gamma is a 2. And also, if we want to know the energy density, then you can just multiply the energy times the distribution function like this. Then after the integration, then you can get the energy density. And pressure is also given by this form. So this part corresponding to the energy momentum tensor of the spatial time. Okay. So I will give some typical typical behaviors of these quantities. So if we consider the relativistic limit, that is, the temperature is very higher than the mass energy, or mass and the chemical potential energy. And in this case, we can set just energy is given by just a momentum. So we can neglect this mass term. Then the number density can be evaluated by this form. Then I will give a precise calculation later, but I just show just a result here. Then finally you can get the number density is proportional to the temperature cubic, and also some factors. And here the upper part is the boson, and the lower part shows the fermion part. And also you can calculate summary, and the energy density is given by temperature proportional to the temperature power of 4. And also the pressure is also proportional to the power of 4. But the coefficient is slightly different. This difference of the coefficient is just you take the ratio of the pressure and energy density like this. Then this gives the 1/3. So that means that this is very famous relation on the radiation equation state. And also, if we want to know the non-relativistic limit, so this case is the energy is almost given by mass term, and also this mass term and the chemical potential is much larger than the temperature. Then we just put the energy is given by the mass term and kinetic energy, this coming from the momentum. Then this part, in non-relativistic limit. So for example, this energy, this part becomes very large, so we can use the Maxwell-Boltzmann distribution, and using the energy is given by this one. Then, and after using this approximation, then integration. So you can give an integration with the Gaussian integration. Then finally you can get the number density is proportional to temperature of the 3/2, like this. And also, if you consider the energy density, then you can get this one. And also, pressure is given by this one. So I will explain this physical meaning later. But now you have to care that if you take the ratio of the pressure and the energy density, like here, then so this ratio is very small, because now we are considering the temperature is very smaller than the mass scale. So in the matter of the equation state becomes, this ratio becomes almost 0. Okay, so I will give a precise calculation of this. So at first, how do we calculate this relativistic limit? And so, for example, the number density, then so just you use this approximation to here, and also here the universe is almost we are assuming the homogeneous background. So there are no special direction of the momentum space. Of course, the normal spatial space, also the momentum space has also homogeneity. Then you can integrate over the angle part of the momentum. Then so you can get this factor, so 4 pi, and times the momentum part. then just you make this calculation, then it's okay. But how do we calculate this integration? And if you take once you replace this momentum integration variable by this x is defined by we're saying roughly the momentum normalized by temperature. Then this integration changed to here, like here. So you just consider this part. Actually, this integration is well-known integration. So if you just at first you consider the minus part, I mean the bosonic case, then actually this type of integration is obtained just you expand this denominator by like this. So very saying roughly the very simple geometric function. Then so after expand this part, then you make the integration over, then you can get this factor with a gamma function like this. And this part becomes the z function like this. So finally, you can get this part is given by this part. Here the n equal 2, so you just put this, here is a 3 and 3. And you can realize the previous result. Then once you know the general form of this part, then you can also get this result. So but the not 2, but the 3 here. And also, if we want to know the Fermi case, I mean that here is a plus. Then it is so to understand this, then it is better to consider this integration can be changed if you consider if you replace this integration variable x to the 2x, then this integration changed to like this. So x changed to here, and the integration measure is changed to 2. So it's more additional 2 factors appears. And actually, you can decompose this term to like this, and also make the fraction partially this fraction changed to like this. And this first part is given by represented by the bosonic integration again, and remaining part is the Fermi integration we want at first. And using this relation, then you can get this Fermi integration. This is given by this formula. Then finally, if you use this formula to here, then you can get this relation. Okay. And the previous result is for the non-relativistic limit. Relativistic limit. And now next we consider the non-relativistic limit. So this is very, very simple. Just you consider the Maxwell-Boltzmann distribution function here. Then so you use the expansion by the mass, or by you expanded this energy by the mass, and make the make the Gaussian integral here. Then you can get finally, just I put the result here. Finally, you can get this relation. So I have to emphasize here that this previous result, I mean, a relativistic case, the result is proportional to the power of 3 of the temperature. But here, of course, it depends on the power law here, but this exponential suppression is very big. So actually, the number density of the non-relativistic limit is very suppressed compared with the relativistic particle. And also, so this energy density and pressure is obtained in the same manner, but the result has some meaning of the very important meaning of the physics. And actually, the final result is here, but you can represent this part with number density. Then, I mean, this part is just a number density. So we can relate the energy density is given by number density times these factors. Actually, this result is very, very low because the first term is just the mass energy of the particles, and also the second term gives the internal energy relation very well known in the non-relativistic Newtonian case. And also the pressure is the final result of the pressure is given by this part. And using this representation of the number density to here, then finally you can get the pressure is given by this form. And actually this form is well known if you multiply the volume in both equation side, then you can get the PV equal NKBT is obtained. So this is very well-known relation in the chemistry. So this is very used as the equation of state for some liquid or gas or something. Okay. And also, so I explained about the some dynamic variables for the number density and energy density and pressure, but there are another very important quantity, some dynamic quantity. It is the entropy. And actually, if you use the first law of the thermodynamics, then so we use this equation or the relation, and also if you use the energy, internal energy is given by energy density times the volume. Here the V means the volume, and also the entropy is given by the entropy density times the volume, and also total number is given by the number density times the volume. So we separated everything volume from the original value. Then, so you can get this relation. And also, if we assume all the thermodynamic variable is controlled controlled by the temperature and the chemical potential, like this. Actually, this is true because as long as we consider this variable by the distribution function, then the variable is only written by the temperature and the chemical potential. So this assumption is very reasonable. Anyway, so if you use this assumption with this derivative is use the chain rule like this, and using this relation to here, then you can get this. Finally, you can get this relation. So this should be 0. So this term should be also 0. Then this final relation, the coefficients for the volume, gives you can represent the entropy density is like this. So actually, once you know the energy density and the pressure and the number density with chemical potential and the temperature, then the entropy density is automatically obtained using this formula. And so using the previous result for the radiation dominant case, then finally you can get the entropy density is given by like this. The important thing is the dependence of the temperature is the power of the 3. And also another equation also gives us some result. And for example, this equation gives the relation for the entropy density by the differential of the pressure by temperature, like this. Another equation gives if you take the derivative temperature by chemical potential, then it provides the number density. But by the way, in this lecture of the cosmology, this is very important. So you have to mind this relation here. And also, I have to mention the relation between the thermodynamics and Einstein equation. Actually, the Einstein equation gives the continuity equation of this. So if you take the derivative of energy density, then you can finally you can get this equation using the Robertson-Walker metric. Then so using this equation and multiplying the scale factor power of 3 like this, then so finally you can get the time derivative of t, time derivative of this term plus pressure times this part is 0. So this scale factor cubic means just a volume. I mean the physical volume. And also as I said, the energy density times the volume is the internal energy, so we can write the E. So this equation says the dE plus PdV is 0. So this result, if you use this result to the first law of the thermodynamics of the original equation of this, and here this part becomes 0. Then finally the equation remains this part and this part. And also if you make the ds differential of s is given by only the ratio of the chemical potential over the temperature times the differential of number. And actually, in the history of the universe, in the almost time, the chemical potential is very, very smaller than the temperature, and also almost a particle number is conserved unless some explosive particle production happens. So actually, this fact says that the total entropy of the universe is approximately conserved. So this result is very important. Okay, so using this conservation law of the entropy, actually this property is very useful for cosmology. So I will give an example here. So now we consider the temperature is the 1 MeV scale universe we consider. In this temperature, then the universe is radiation dominant. So almost a particle behaves as a massless particle. And in this temperature, actually there are several particles in the universe. One is the electron and its antiparticle, the positron, and also the photon and neutrinos. So I plotted here the pink particle is electron, and also the green one is the positron. And also this orange color is photon, and this white particles are the neutrino something. And if the temperature is very much higher than the 1 MeV scale, then actually this neutrino and electron is can scatter together like this, and also the electron and the photons can scatter together, and also actually the electron and positron can scatter together. I mean, scatter means they annihilate together. Then it's convert to the photons. Actually, this reaction happens. This left to right process, and also the right to left process is also happens, or in almost same probability. So after that, if the temperature becomes a 1 MeV, then actually this electron and the neutrino reaction rate doesn't happen in this temperature. So actually, in physics, we can understand this physics as follows. So if you focus on this neutrino, then if you consider this the case of the very high temperature more than the 1 MeV, then this neutrino has some interaction area, and if this neutrino goes straight like this, then this the area of the interaction goes through here. Then some volume of this cylinder, including, and if the neutrino includes some particle, for example, here the photons and the electrons and positron is including here, but the neutrino can only hit to the electron and positron, not photons. So I mean this positron and electron. Then this neutrino can react to electron and positron. In physically, so on the other hand, in this case, of course, the temperature goes down, then universe is expanding, so the temperature is also drop down, and also the energy density or the number density is also reduced. So like this picture. So if we consider the same situation, then the number because the number density is smaller, so this inside of the cylinder does not hit to the electron or positron here. So physically, how do we calculate this is, so just you give the length of this size. This is called as the cross section. This is the physical value of the area. And also, if this neutrino has the velocity, and this velocity goes through this delta t, this is the time. So very saying roughly delta t is given by the age of the universe. So you can just get the 1 over Hubble parameter. This is the the volume of the. So if you multiply this sigma and the V over H, then this actually this gives the size of the interacting. Then probability is given by the just a number density times this volume. So just you can compare this value is larger than 1 or smaller than 1, then so you can discriminate the interaction happens on. But this cross section is calculated from the elementary particle physics or something. So that is another story. So I skipped the detail of this calculation. But anyway, so in the if the temperature becomes 1 MeV, then neutrino interaction doesn't happen. After that, temperature below than the 0.5 MeV, then next in this situation, the electron and positron annihilation happens, but the back reaction doesn't happen because the mass of the electron or positron has this value 0.5 MeV, and if the temperature goes down below the this value, then actually the initial photon do not have the enough energy. So very small. In that case, the this photon energy do not reach to the back reaction needed required energy. So this process doesn't happen. So in this situation, so we can calculate the entropy here. In the case of the temperature is larger than the MeV, then this entropy is given by just using this formula. But the almost coefficient is common, but the difference is the degrees freedom. So we calculate the degrees of freedom of the electron and the neutrino. Electron is here and the neutron is here, and also photon is here. And on the other hand, so if the temperature goes down to very small, so I mean the very smaller than the 1 MeV, or I have to say the 0.5 MeV, then the almost electrons positron is disappear because of the annihilation together. So it almost they almost convert to the photon. By saying roughly, this photon has received the energy from the electrons. So actually, the photon is heated up rather than heated up than the neutrinos. But anyway, if we know the entropy is conserved, so this entropy is almost equal to this total entropy. Then, so you can calculate the neutron entropy and the photon entropy. But as I said, the photon receives the energy from the electron, so the temperature could be different from the neutrino. So we have to separate this temperature. And the common temperature before the temperature is larger than the MeV, then this common temperature is almost evaluated by the neutrino temperature. Then finally, you can get the temperature ratio of the photon temperature and the neutron temperature. Then this gives this result. So as I said, the photon temperature is slightly larger than the neutrino. Actually, this is very good prediction for the neutron temperature in present. The CMB observation shows the photon temperature is given by around 2.7 Kelvin. But if you use this relation, then neutron temperature is given by this value. So maybe this value this value should be checked in future, but I think this observation is very hard to observe. Okay, I explained about the some dynamic variables, and next I give a very important concept of it called as the effective degrees of freedom. But so at first we focus on the Hubble, and according to the Friedman equation, then Hubble square is given by energy density times something, and so actually, so now we are considering the thermodynamic energy density. Then this thermodynamic energy density is given by, so we are using the previous formula for the energy density. Then, and we separate the species of the particles by the relativistic bosons and relativistic fermion, and also non-relativistic particles. Of course, this non-relativistic particle is can be distinguished by boson and fermion, but the difference of the calculation value is almost same, so we do not separate together. But anyway, so if you use this formula to here, then finally you can get this result. But as I said, the non-relativistic mode is suppressed by exponentially by this factor, so called as the Boltzmann factor. Then this term can be negligible. And finally, you can get this part has a common value by this part. So I pick up this value and times some degrees of freedom. So this G star is defined by the original definition is just given by you divide the total energy density divided by the one particle, 1 degrees of the energy density, like this. Then, so using some approximation, as I said, the relativistic particle is dominant. Then, finally, you can get this is called as the effective degrees of freedom defined by the energy density. G star is almost approximated by like this. So the physical meaning is that, so how many of the number of the relativistic particle, and the result is just if there is no difference between some particles to the photons, then this can be negligible. This part is just a 1. So just a total degrees of freedom for the boson and the fermions. But the fermion has the extra factor 7 by 8, like here. So previously, I defined by the energy density, but also we can define similar quantity by entropy. So using this entropy formula with this calculation, then so using some we use some approximation by the chemical potential is very small comparing to the temperature, and also this exponential factor is also very strong, then finally we can get a similar result to the degree of freedom defined by the entropy. But the difference is, so previous result shows the power of 4 here, but this case shows the power of 3. This is very a little bit difference. But this difference is important for the low energy. Sorry. Okay, so I give us some example point. So we can calculate the G star and G star S using the standard model particle contents. Actually, if it goes to the temperature is infinity, then almost particle means we are considering the standard model particle. Then there are the contents of the quarks and electrons and neutrinos, and also the massive gauge bosons. So this is called as the W and Z. And also, we know the massless gauge bosons like the photons and the gluon, and also the final particle is the Higgs boson. This is also has the degree of freedom of 1. Then, so we collect the all the particle degrees of freedom. Then finally, we can get the degrees of freedom is given by like this. Just we count the degrees of freedom for all the contents, and also this value is agreed with together. And so next point is the temperature is around the 10 MeV scale. Actually, in this time scale, only the electrons and the neutrinos and the massless gauge boson of the photon remains. So almost particle contents is erased because they are very massive, and also, of course, a part of the quarks up and down and the gluon here is remained, but they form the nucleons or something, and nucleons becomes very massive. So as I said, the massive particle can be negligible for the degree of freedom. So just we consider this particle contents, then you can finally get the degrees of freedom is around the 10 or 11 or so. So this case also gives the same degrees of freedom. Finally, we consider the limit of the temperature 0. Then the difference is, as I said, the electron particles are erased because they are annihilated together, and that goes to the photons. So now we remove the electron from the previous result. And also, as I said, the neutrino and the photon temperature of the neutrino and the photon is different because of the energy of the electron converts to the photon. So we can calculate the G star and G star S separately. Then finally you can get this value. The G star is 3.36, and also the G star S is more higher, but they close to the 4. Okay, so this plot shows the exact calculation with that approximation, as I said. But this horizontal line shows the temperature, and left side is high temperature, and the right side means the low temperature. And also this vertical vertical line shows the G star or the G star S. Then if you goes to the high temperature limit, then as I said, this value close to this value. And after that, so as I said, around the 10 MeV scale, so around here, then the degrees of freedom shows the almost close to the very close value to the 10 to 75. And finally, and this value goes to this plateau, and each value shows this value. Okay. And finally, of this section, so I give a relation between the temperature and the time scale in the radiation dominant universe. So using the Hubble using the Friedman equation of for the Hubble scale, then Friedman equation gives this relation, and also this radiation dominant energy density is given by this formula. So you can solve this Hubble square is this. Then finally you can get the Hubble is proportional to the power or temperature power of 2, like this. Actually, why we can calculate like this easier is, so we define the G star here. So the calculation seems becomes easier, but all the information for the particle is including here. And also, the Hubble is just given by the A dot over A, and now we are considering the radiation dominant case. So the scale factor is given by these values. Then Hubble is just given by the 1 over 2t. And applying this result to here, then finally you can get the relation between the time and the temperature. And the final result is this. And if you use some exact value here, then the temperature is given by numerical this parameter. So we're saying roughly 1 second is relating to the 1 MeV scale. Okay. So I explained I defined the effective degrees of freedom by energy density and the entropy. And finally, I give us some story for the application example of the thermal history. Actually, this this figure of the history is already showed before, and now we are focused on here. So as I said, the 1 second that is relating the 1 MeV temperature is here. So actually, this in the thermal history, so this scale is relating to the Big Bang nucleosynthesis, but now we are considering just very later than the BBN. So we are considered this it is called as the matter radiation equality scale. So from this name, so we are considering that when the matter and the radiation energy density becomes same factor, then as you know, the half can be derived by the by the density parameter like this. So the matter component of the energy density is proportional to the power of 3 of the scale factor like this. And also the radiation dominant radiation energy is proportional to the power of 4. And normally this part is negligible for the precisely this curvature part is proportional to the A power 2, and also the vacuum energy is proportional to almost constant. So this do not have the scale factor dependence. But in any way, if we consider the small universe, that means the A is small, then this radiation part becomes dominate like this. And so the expanding universe, then sometime this part dominate than this part. Then the dependence changed to like this. And finally, that is the corresponding to the current, the present universe. But finally, the energy density is dominant by the vacuum energy density. Then the evolution changed to like this. So now we consider this equality point. So at first, we consider the radiation energy density from this side. Then, in this case, of course, the radiation dominant universe. So that this is given by the thermal equilibrium energy density like this. And also, on the other hand, this energy is in the case of the matter dominant case, then we can calculate this energy density by like this. So at first, we consider this property. So matter energy density is given by proportional to the power of the 1 over A of power of the 3 of the scale factor A. And also, now, actually, the definition of the density parameter of matter is given by like this. So we change this rho m current value to be like this. And also, the scale factor part. Actually, we know that we use the entropy conservation here. So you multiply the numerator and denominator in both sides. Then this part is the total entropy. So this total entropy can be regarded as the conservation law. Then we can use the current value. Then you can divide this scale factor here. Then only the entropy is remained, and entropy dependence, time dependence of the entropy remains this part. So this scale factor of power of 3 can be changed to this part. So finally, this energy and this energy, when this becomes same, then we can connect the equal this green one and blue one and green one, and like this. So we call it, the temperature is written by TEQ. And solve this equation by TEQ, then finally you can get this result and use this current value, that's current observation value. Then finally you can get the this temperature of the matter radiation equality is given by the 1 eV scale. By saying roughly, this is corresponding to the 10,000 Kelvin. And as I give a relation between the temperature and the time, then you can change you can translate this temperature to the time scale. Then that is relating to the by saying roughly the 30,000 years. Okay, so after you using the energy density conservation, entropy conservation is applied, then you can calculate the matter radiation equality. This happens the 30,000 years before. And next, we consider the next time era. It is called as the recombination. Here, actually, what happened is that before this time scale, then there is some neutron and proton, or the deuteron or helium or something exists, and they are flying freely. But after this recombination scale, then the deuteron or the proton or the helium absorb the electrons. Then it forms the atom like this. Then after that, the universe, whole the universe becomes neutrality. Then photon can go straight. So that means the universe becomes transparent. So that as a result, the CMB photon is observed like this. So we estimated this time scale and the temperature scale later. So actually, as I explained just before, so the situation is that we have some photon, electron, proton, and helium or deuteron or something in this system. Then of course in this situation the photon can flying, but this photon is hitting to the electrons or proton or helium. So if you catch these photons, but this photon's trajectory is very complicated, so we cannot get the exact information of the before scattering. But after the recombination, then of course the space is expanded, so the density is also diluted. But the most important thing is that the proton or the hydrogen absorb the electron, so it's form the atom like this. Then there are almost electron is absorbed. So sometimes photon hit to the electron. This electron, very rare electron exists, but it is very small. But almost photon can go through straight like this. So finally, this photons has the information for the very earlier era. So this can be observable like CMB photon. So now we are considering when this electron capture happens. So now we are focused on this interaction in the equilibrium. So actually the electron and the proton is form the hydrogen and the which emits the photon. This energy scale is relating to the ionization energy. And now we are considering when this interaction decouples. At first, we focus on the conservative quantities. Actually, there are several conserving quantities here. The first one is chemical. So this system is in chemical equilibrium. So the chemical potential, the total chemical equilibrium, total chemical potential is conserved. So I mean the electron and protons chemical potential is same to the total hydrogen and the photons chemical potential. But now the photon chemical potential can be regarded as the zero. So we can just consider this electron and proton summation of this is equal to the hydrogen. But still, we don't know the how largeness of this chemical potential here. So I will explain how to attack to this problem later. And also, the second conserving law is the charge neutrality in the universe. Because so electron number and proton number is same, so we can connect equal together like this. And also, we can consider the partial baryon number is conserved. So that means the total nucleons number, we can say. And this hydrogen's baryon number, I mean hydrogen's nucleons number, is just given by the proton and the hydrogen. And actually, this value is known as around the 76% of the total value, because actually this fact is known by if you consider the Big Bang nucleosynthesis theory. In this theory, actually the final baryon number distribute to the around the 75% baryon consists of the hydrogen, and the rest 24% is the helium. But here we just use this result. And okay, so in order, so we use this three conserving quantity later here. But at first we focus on the ratio of the electron and proton and helium number density. So why we consider? I will consider why we use this quantity. But just we calculate this value with this formula. So now the electron, proton, and the helium is non-relativistic particles, so we use this. Then we can get this ratio is given by like this one. So this is the reason why we consider is here that. So just appear the chemical potential combination is here, appears here. So we can eliminate this part because the chemical potential conserved together, because chemical potential conservation law shows this part is zero. And this part, I mean the energy difference between all the mass scale of the electrons, proton, and subtracting by the helium energy, then it gives the ionization energy. I mean the 13.6 GeV, 13.6 eV. This is the one side. So I just I calculate this value by thermal equilibrium value. And also, so next step is we consider same quantity, but we use the conservation law here. At first, we consider this hydrogen's number density by using the barium number conservation here. So we can eliminate the dependence of the NH. And also, actually, we can consider that this proton and proton number density is same to the electron. So we can change the NP is NE like this. And also we define the ratio of the ratio of the number density of electron over the barium. And this quantity is called as the ionization rate. So if this value is the 1, then so electron is this 1 means this barium and the electron has the same number density. So ionization doesn't happen here. But the Xe becomes 0, then number density of the electron is 0. That means the almost electron is absorbed to the proton or other barium particles. So X equals 0 means the ionization happens already. And also we define the this YV. This Y is called as the yield value for the total value. Then we consider this. We define this Y is a ratio of the number density of the barium by entropy density. Actually, if you multiply the scale factor cubic on the numerator and denominator here, then it becomes conserving quantity for each value. Then we can replace the present value. But anyway, so after we use this value to here, and using this MB, the partial barium number is given by the total barium times the sum ratio. Then we can get this factor is given by ionization rate and the conserving value times entropy. Oops. Then, so I get the two results using the thermal equilibrium value and also using the conservation law. So we can connect equal together like this. And so we use this energy entropy density is given by the formula of the temperature of power of 3 like this. Then so you can make the equation for the ionization rate, and it can be solved. So after so this plot shows the result of this equation. So I change the value of the temperature by Kelvin unit, and this particular line shows the rate of the ionization. Then you can see that this transition happens between the temperature scale of the 3000 to the 4000 scale. And so if you take this times this ionization happens at the 3000 Kelvin, then this is corresponding to the this time scale. we're saying roughly the 3 and 80 and 1,000 years. But this calculation is the very this calculation includes a very rough calculation. Is we are considering the very rough calculation. So if we want to precise a more precise calculation, then you have to follow the Boltzmann equation. But I do not touch here because it is very complicated. Okay, so today's lecture is finished. So next I will give my impression. But today's finished.